Lab 5 buoyancy. Lab number 6 reports are due in lab next Tuesday, and I don't specifically remember who goes at 2 o'clock and who goes at 3 o'clock, but I'll try and figure that out. I'll backtrack and we'll let you know on Tuesday. I think it's Group B at 2 o'clock, but I'd want to double check. So what do you think? Who goes first? Group A goes first. Now, see, I'm seeing some no's in the back. I'll look back through that. I'll let you know on Tuesday. You're scheduled from 2 to 5, and so, yeah, you'll be out of there sooner than that. Homework 4A is listed. It's due on Thursday, the 10th of October, so a week from today. The next homework assignment's due. What we're going to be covering in Chapter 4, it's, in a lot of ways, one of the most important chapters in the book. Chapter 4 is where we finally start to talk about moving fluids. And until now, we've been talking about fluid properties and hydrostatics. But water is not moving a very small fraction of the time. Far more common is for water to be moving from place to place. And the reason why engineers are asked to do work is a lot of times to move water, maybe from a water treatment plant to somebody's home. And so here in Chapter 4, we're finally going to learn some of the laws that enable us to consider the movement of water. So it's a really important chapter. And what we'll be talking about is the movement of particles, which will sometimes calculate the movement just of the actual particle itself. Sometimes we'll break it up into elements. But the reason why fluid motion matters is because a lot of the structures in civil engineering, whether it is a dam or spillway for a dam, or the penstock for a dam, or maybe water pressure, water lines underneath the road. A lot of the things that engineers are asked to design are related to moving fluids and large quantities of it. There are two different ways of trying to keep track of the movement of particles, and doing flow visualization and flow tracking. And historically, the first of these approaches was called the Lagrangian approach. To answer the question, what is the fluid velocity? The approach here would be to track a particle in 3 dimensions. And the Cartesian coordinates of a particle would be represented by their I, J, and K coordinates, or X, Y, and Z coordinates. What you'll notice, though, is that there are a lot of particles that in a pipe where water is moving through the pipe, there are billions and billions of particles moving at any one time, and so it's computationally very intensive to try and keep track of individual particles, especially when you're having to calculate the velocity as a function of 3-dimensional movement and the change over time. And so the challenge with the Lagrangian approach is just keeping track of all of those particles. And so the Eulerian approach is to, instead of keeping track of individual particles, is to break a flow area up into elements. And so it's to represent the flow area with a mesh, and then to assign behavior within the mesh to all of the particles that are inside that volume at a certain time. And so if you divide a flow field up into elements and you say that it has certain windows, and you look at what's happening at the intersection of those windows, the flow particles are going a certain direction. And so it simplifies, and it's a way of averaging. Instead of all of those particles individually, you say all of the elements of water that are inside of here you're going to represent with a single flow direction, a single acceleration, and that becomes representative of all the particles. And so the velocity at the field is related to its location at a certain time and its time as the flow progresses from the beginning of a time that you're analyzing to the end of the time increment. Flow visualization is a way that we can get a lot of information about what's happening in the flow field. And who'd like to take a stab at describing what's happening in this picture? What are we looking at? All right, it's a wind tunnel. You know, once in a while when I ask that question, people will be able to identify the car. I have no idea what car that is, but yeah, I don't know. I think when I was teaching over in the UAE, a couple of my students probably had this car or something. A lot of rich students over there. But okay, this is a wind tunnel, and what's that? Right? It's smoke, and you, by virtue of the smoke looking the way it does, you can tell that the air is moving, right? That this is a wind tunnel, and it's not that the wind tunnel is shut off. The wind tunnel is on. And can you tell whether the air is going this way or if the air is going that way? How can you tell that the water is going towards the left? It's more dispersed, right. Dispersion means that the smoke is spreading out over time. And so this is the beginning of the smoke, and this is the end of the smoke. All right. What does the curvature in these smoke lines tell us? How fast? How? Well, what does it mean when they're getting closer together? Because you notice that right here, the smoke lines are far apart, but then here the smoke lines are closer together. Is there anything that can tell us? All right, the bottom line is getting pushed up. What's that, David? Resistance. What do you mean by that? All right, the car is interfering with the flow of the air. All right. Well, what we're looking at is flow patterns, and we're going to be talking about streamlines, streak lines, and path lines. First of all, what we are just looking at are considered streamlines. And if the fluid is water, then there can be two different kinds of streamlines. There can be streamlines in open channel flow, and so here the figure on the left is showing what if water is flowing downhill. And these little hash marks here means that it's meant to represent the ripples of water, and so it's a free surface of water, and you can see that the streamlines are parallel right here. Go ahead, do it. Get it over with. Rip the Band-Aid off. All right. The fact that they're parallel means that the velocity is constant and that the fluid isn't increasing its speed. And so things are sort of, here is a steady flow. Now, the enclosed channel, like dump them onto the paper so we don't hear the bag. There we go. All right. When the channel is enclosed, this is a closed conduit flow. So it's a circular pipe, but we're just looking at a cross section. And again, the streamlines are parallel here, which means that the fluid isn't accelerating, that the velocity is constant. And so right now, all we can tell from this diagram is that we don't know what the magnitude of the velocity is. And it may be that it's 1 foot per second, or it could be 10 feet per second. We can't tell from the streamlines the absolute magnitude of the velocity. But what we can tell by looking at this is that the velocity isn't increasing, that the velocity is constant in the direction of flow with respect to position. Okay, here's some other flow patterns. Now, from these streamlines that have just been shown, we can tell that the direction of the velocity is changing because look at these streamlines are getting closer together. And so if the streamlines are getting closer together, then that means that the relative velocity is increasing, that it's speeding up as it goes towards this orifice. And so there's an opening in the tank. The water is speeding up as it flows out of the orifice. Another thing that the streamlines can show us is that if a streamline stops, that indicates a stagnation point where the pressure would be a little bit higher than surrounding the rest of the airfoil. So here on the front part, the leading edge of a wing, there's a stagnation point where pressure is high, and you can represent that with a terminating streamline. Finally, in these two depictions, the velocity is increasing. You can see that as the streamlines are getting closer together, that means that the velocity is increasing, and so that's acceleration. A certain kind of acceleration. We're actually going to be talking about 3 different kinds of acceleration in this chapter. Usually in physics, what's the definition of acceleration that you're most commonly acquainted with? Acceleration is what? So it's the change in velocity, the change of time. Right. Well, that's not what this is talking about. This is talking about a different kind of acceleration because in this picture, Flow could be, the velocity could be constant with respect to time, but yet there would still be an acceleration. In this case, this diagram, it's an acceleration with respect to position. That the velocity is increasing not over time, but the velocity is increasing as the flow moves from left to right. And there's acceleration here too. Remember that velocity is a vector, and it has both magnitude and direction. And so in this rotational flow, as the water flows around in a circle, this rotational flow has an acceleration because the direction of the velocity is changing over time. And so the streamlines aren't parallel, but it's not because it's speeding up, it's because the direction of the velocity changes as it flows in that rotational manner. It's really important for us to classify flow into different categories. And the different categories of flow, we use different equations to handle flow in different categories. And also there are different types of acceleration that goes along with these different categories of flow. The first of them that we've already taken a look at is uniform flow. When the uniform flow is going, that means that the velocity is constant along the streamline. So with respect to position, the velocity isn't changing if the streamlines are straight and parallel. So you can see dv ds. S is meant to mean the position in some direction. So the change in velocity with respect to position is 0 in case of uniform flow. If the flow is non-uniform, that means that the velocity is changing with respect to position. And so we can see here that the diagrams where the streamlines are either coming together or getting further apart, that means that the velocity is changing with respect to the position along the streamline. Or here, this is another case of non-uniform flow because the direction of the velocity vector changes over time. So non-uniform versus uniform is talking about how velocity changes with respect to position. Another way that we can classify flow is what's happening over time. And that's the definition of acceleration that you're already most well acquainted with, how the velocity changes over time. And so if velocity is constant over time, we call that steady flow. And if the velocity is not constant over time, we call it unsteady flow. Now, I had pictures on the last page to illustrate uniform versus non-uniform. It's possible to depict that with a picture. Why is it that when I'm comparing steady and unsteady flow, I don't have a picture for that? Why is it that just a single photo can't show you whether you can't know by looking at a picture whether the flow is steady or unsteady? Exactly. That's right. So a photo is just at one instant of time what the velocity conditions are. And so the way that we'd need to differentiate steady versus unsteady is with a series of images, like a video or time-lapse photos. That would help us to know if conditions were unsteady. So if we had a river and we were looking at the water elevations, and maybe at 8 a.m. this is the water, and then at 10 a.m. this is the water elevation. You know, from that time-lapse photo we could tell there's unsteady conditions because the velocity or the depth, some component of the flow is changing over time. That means it's unsteady. But let's say that in addition to that, there was a change in slope. What if there's a part of the channel that's steep and then a part of the channel that's shallow? And so it was, you know, shallow water and then it got deeper. And this was what happened at 8 a.m. But then at 10 a.m. it was like that. So this would be both unsteady and non-uniform. So you can have combinations of each of these different types of flow. They're not exclusive. It's not like if the flow is steady, it can't be uniform or non-uniform. There can be any number of these combinations. So you can have steady unsteady, uniform, and non-uniform. So if the flow is steady and uniform, then that means, let's take a look at one of these uniform pictures. So if it's flow going through a pipe that's a constant diameter, if it was both steady and uniform, it means that the flow rate is the same now as it'll be in the future, that it's not changing with time and the velocity doesn't change with position. So constant with respect to time and position. If it was steady and non-uniform, so steady means it's not changing with respect to time, but non-uniform means that it is changing with respect to position. So here is our non-uniform. Non-uniform flow, but if it's steady, that means that an hour from now, maybe, the velocities are going to be the same that they are now. And so remember, steady versus unsteady is all about time. How do conditions change with respect to time? Uniform versus non-uniform, that's talking about position. How does velocity or some other aspect of flow change with the position in the flow field? Any questions so far? What if velocity is changing? What do you call that? Velocity is changing with respect to time. Acceleration. What we actually are going to call that is we're going to call it local acceleration to differentiate it from other kinds of acceleration. So something that's velocity changes with respect to time, what causes unsteady flow? It's caused by local acceleration. Or we can class, maybe it's not that it's caused by the acceleration, but we can define the acceleration in terms of the change in velocity with respect to time. That's local acceleration. Okay, before we get too much further into uniform versus non-uniform and steady versus unsteady, let's talk about the difference between laminar flow and turbulent flow. These are maybe things that you've heard about before, laminar flow versus turbulent flow. And it's a way of trying to distinguish how much turbulence there is in the flow field. And it's a function of the velocity. In the case of an enclosed pipe, it would be a function of the diameter. And then also it's a function of the fluid properties. So you can calculate whether the flow is laminar or turbulent with something that's known as the Reynolds number, RE. And so the Reynolds number is the density of the fluid multiplied by the velocity that the fluid is moving at, multiplied by the diameter of the pipe, and then you divide by the viscosity of the fluid. Anybody remember what the difference between viscosity and kinematic viscosity is? Remember, this is the symbol for viscosity, and this is the symbol for kinematic viscosity. Very good. So viscosity divided by density gives you kinematic viscosity. And the reason why I bring it up right now is that's the formula for Reynolds number. You can say that the Reynolds number is the density, velocity, diameter divided by viscosity. Or you can say it is velocity times diameter divided by the kinematic viscosity. And that's a little bit simpler. You know, it's got one less variable there. Yeah. Well, here's the density. What we've done is we've exchanged the kinematic viscosity, because remember that this says kinematic viscosity is viscosity divided by density. So we've just rearranged and substituted in. So we're taking this out and replacing it with that, because this has both viscosity and density. Let's make the substitution. So if instead of viscosity, we would have, instead of kinematic viscosity, we'd have viscosity and density. And so then we, I'm sorry, viscosity and density. So if we moved that back up into the numerator, then that's the same as what this was. Yeah. So we're going to replace that instead with kinematic viscosity. So the typical kinematic viscosity for water, if you don't have other temperature information, 1 times 10 to the minus 6th meter squared per second. That's just a typical about 20 degrees Celsius viscosity of water, kinematic viscosity of water. So if you want to calculate the Reynolds number, you multiply the velocity times the density, then divide by 1 times 10 to the minus 6th, and you'll very quickly be able to have the Reynolds number. So let's give this a try. Let's calculate an example. Let's find out if we had a pipe diameter that's 2.5 meters in diameter, and the water is moving at 0.1 meters per second, then what is the Reynolds number for that? And once we calculate the Reynolds number, we'll know whether the flow is laminar or turbulent. For a velocity of 0.1 meters per second and a pipe diameter of 2.5 meters, if we divide by the kinematic viscosity of water, 1 times 10 to the minus 6th meters squared per second, we get the Reynolds number is 250,000. So Morgan, what are the units of a Reynolds number? What he said? Okay. Yeah, it's unitless. It's a unitless, it has no dimensions. So 250,000 puts us into the turbulent range. And so we can say here turbulent. And what turbulent means is it means inside the pipe that the water is sort of bouncing off the walls, so to speak. That rather than, if there's a disturbance in laminar flow, if the flow is laminar, that means it's moving so slowly and so gently that if for some reason water got out of line, it would just get back into line again. That the conditions are quiescent inside of the pipe when conditions are laminar. The water is slipping over, each different layer of water is slipping over the other layer, and that blue line that's nice and smooth there, that's a velocity profile. What's that saying is that the velocity in the center of the pipe is the highest, and the velocity at the edge of the pipe is 0. Why do you suppose that the velocity is the highest at the center of the point? What is it about the center of the pipe that allows it to have the greatest velocity there? All right, it's the point that you're furthest away from the pipe friction. Remember when we were talking about a plate being pulled through liquid? I think we had a tank of glycerin. and we were pulling that plate through a liquid, and there was a velocity distribution where the liquid that's right in contact with that plate is moving along with the plate. It's touching the plate and it's getting dragged along with it. And so here inside of the pipe, at the edge of the pipe, since the edge of the pipe is stationary, the water that's touching the edge of the pipe right at the boundary layer also has a velocity of 0. But then there's a layer of water above that, and that layer of water is slipping a little bit faster than the layer below it. The layer below it is 0. And so there's a very orderly transition and an increase in velocity until when you're the furthest away from those flow resistance surfaces, from the pipe walls, the velocity is maximized. And there's a parabolic distribution for the velocity profile. In the case of turbulent flow, instead of having this very orderly movement of the water's moving so quickly that there's a lot of disturbances and a lot of turbulence. And so water is reflecting off of the walls, and then there's some of it down here coming together, and then that'll go off in some random direction. There's a lot of uncertainty to the flow field. And what they're representing with the velocity distribution here is they're showing that there's a lot of variation over time. If you look at this particular location right now, it looks like it's a little bit less than the average. But if you look at this location in 3 seconds, it may be a little bit faster than it was 3 seconds prior. This dashed line is representing sort of the average velocity profile over time. And you'll notice instead of having more of a bullet shape, you notice this bullet shape that there is for the velocity profile, it's a lot more flat in the case of turbulent flow. And that'll be important when we talk about the movement of flow and how we calculate it with something called the energy equation. But this U bar is referring to the average velocity, and then U is the velocity at any one time.
What would happen if the pipe itself,
Uh-huh. Yeah.
Would that increase this flow rate or decrease it?
I think it would probably induce more turbulence, because what you'd be doing is you'd be causing the water to rotate as it flows, and so that would probably add resistance to the flow. The best conduits for flow, meaning you get the most flow, are those that are very, very smooth. And so any interruption to that, even if it's a regular pattern like rifling, would just induce more turbulence. One thing I'll point out is that for the laminar flow, the flow at the peak is double the average. If you draw a line to try and find out what's the average flow, the flow at the center line in laminar conditions is twice the average velocity. All right, part B of this example is what's the maximum flow velocity that you could have in order to see laminar conditions. And so if the 0.1 meters per second was too fast, that gave us turbulent flow. And by the way, that's not a very fast velocity. Think about 0.1 meters per second. I mean, that's talking 10 centimeters per second. So if you were walking 10 centimeters per second, that's a pretty slow pace. And so water is flowing through a pipe 10 meters per second, that's still going to have turbulence. And that just gives you an idea of how rare laminar flow is. Most of the time when we're doing calculations for like water flowing over a dam spillway or water flowing through a pipe network, almost always it's going to be turbulent flow. It'll be very, very rare for it to be laminar conditions. But part B of this example, what if we want to have, what's the maximum velocity for laminar flow? So max velocity for laminar. And so what we do in that case is we'd let Reynolds number be equal to 2,000, and then we solve for the velocity that gives that Reynolds number. And if the Reynolds number is V d divided by the kinematic viscosity, we're going to solve for the velocity. So that'll be the Reynolds number times the kinematic viscosity divided by the diameter. And that is 2,000, which is the maximum limit for the Reynolds number in order to be laminar. Anything above that, and it's in this transition zone. We'll talk about the transition zone. 1 times 10 to the minus 6th meters squared per second. And then the diameter for a pipe that's 2.5 meters, that means that the maximum velocity that you could have is 0.0008 meters per second. So in other words, the water has to flow at 0.8 millimeters per second in order to be laminar. It's almost stagnant, yeah. We have a device in the lab that allows us to see laminar flow. It's a translucent pipe made out of acrylic, and it's a very small diameter. And you'll notice that for Reynolds number, if the diameter decreases, then that means that the Reynolds number decreases. And so it's a small pipe, and that helps us to be able to see the Reynolds, to find the conditions where conditions are laminar, and we can observe it, how laminar looks when it's flowing laminar. Now, what's between 2,000 and 4,000 is a question that I often get. You know, if below 2,000 is laminar and above 4,000 is turbulent, then what's from 2 to 4,000? That's something called transitional flow. And the conditions will be laminar or turbulent depending on what they were before the flow got into the transition region. So let's say, for example, you've got a pipe and you've got a valve on the pipe that allows you to control the flow rate. So I've got a tank of water, and the water is going to be spraying out of the valve. And so I can open and close that valve and control the velocity of flow through that pipe. So I slowly open up the valve, so slowly that at first conditions are laminar. So the water is flowing laminar because I forced the water to move slowly. But now I'm increasing it, and now the Reynolds number is 3,000. Well, since it was laminar conditions before I got into the transition zone, it will stay laminar unless I either increase the velocity even more above the point at which it transitions into 4,000 for the Reynolds number, or if it was in the transition zone and then I hit the pipe with a hammer, what I would have done is I would have forced a disturbance, like caused a little shock wave that would induce turbulence, and then it would be turbulent. Once I hit it with the hammer, then all of the laminar flow would be in the transition regime. And the same thing is true if the water is moving turbulent and I gradually start closing the valve, and so I'm slowing down the velocity. It will stay turbulent until you get to about 2,000. Because it was turbulent before, it will stay turbulent through the transition zone until you get to the point at which it stops over to being laminar. And so that sort of no man's land between laminar flow and turbulent flow is determined largely by how you got into the transition zone. Did you get there from the laminar side, or did you get there from the turbulent side? All right. So back onto the subject of uniform versus non-uniform and steady versus non-steady. Remember that whether flow is uniform versus non-uniform depends on position. It's characterizing velocity change with respect to position. Now, I know that it's confusing to talk about time and position as though they are completely independent, because let's say that we've got a valve. I'm sorry, not a valve, but we've got a change in diameter here. Let's say we've got a pipe that the diameter is increasing and then it's continuing. And so here we had a small diameter pipe. Maybe the diameter here is 25 centimeters, and then the diameter here is 80 centimeters. So the water was moving along, and then when the velocity when the diameter changed, so is the velocity. The velocity is going to decrease because you've got a larger flow area, so the velocity doesn't need to be as high. So these streamlines are further apart. That means that the velocity is lower. So what happened there was a deceleration. The velocity decreased, and it decreased with respect to position. And so right here, the velocity is of the water, we'd say maybe the velocity is 3 meters per second. Here, the velocity will be less than 3 meters per second. The velocity will have decreased because of the change in diameter. Now, at this one instant in time, not looking at how things are going to be a minute from now or an hour from now, at this one instant in time, there is an acceleration happening with respect to position. And so this is non-uniform flow. Now, at the same time, maybe it is that right now we have 3 meters per second here, but an hour from now it might be 5 meters per second here, and then it'll be less there. So it could simultaneously be both non-uniform and unsteady. The kind of acceleration that we've talked about for when it's respect to time is local acceleration, and the kind of acceleration when it's change in velocity with respect to position is called convective acceleration. And your homework assignment has a problem that has to do with convective acceleration. We'll get into the details of convective acceleration, but I wanted to first of all point out that whether the flow is uniform versus non-uniform, a change in velocity is meaning that there's an acceleration involved, and the name of that acceleration is convective acceleration. If it's going this way, then it's still a non-uniform flow, and the velocity would be slow here, and the velocity would be greater there. All right, so the streamline is what we've seen before. The streamline can tell us the direction of flow, but it doesn't tell us the magnitude. Now, there's a new way of tracking the flow, and that's with a path line. And a path line shows the movement of a particle over time. It traces a path. There's also something called a streak line, and a streak line is produced by continuously injecting some sort of a tracer or a dye. And it tells you the history of flow over time. We'll take a look at an example that compares path lines, streak line, and streamlines. And then on Tuesday, next week, we're going to work an example that compares streamlines, streak lines, and path lines. So I'm going to show you a scenario on the next slide where there's two different time periods. On this next slide, there is before a certain time. So before T naught, the water was flowing to the right. And then after T naught, the water was flowing up and to the right. And so I just wanted to show you that because when I show you the next slide, there's a lot happening all at once and it's a little bit jumbled together. And I wanted to point out that what we're going to be looking at is that the water was moving to the right at a certain time, and then it was moving to the right and up at the next time. So these light blue lines are saying that at first the water was moving to the right. So see these streamlines here. They're saying that for the time before T naught, the water was going to the right. And then after that, the flow field shifted and it started moving up and to the right. So if we drop in like a tin can, think about what would happen if you drop in a tin can. That's going to flow this way, and then it's going to change direction. That's a path line. A path line is just sort of if you were up above taking an aerial photo every certain period of time, every second, then the path line is the path that would be traced by the single particle as it moves in response to the changing flow directions. Now, a streak line is a little bit more complicated than that. What happens with a streak line is instead of tracking just a single particle as it gets pushed around, in the case of a streak line, what we assume is that we're continuing to inject dye at the same point, but then that die is moving around as the flow direction changes. So think about if this is the point of interest. At the beginning, what I did is I started injecting the dye, and then the water is flowing that way, and so it's pushing the dye this direction that I have injected. And so this part of the streamline, this part of the streak line is that first dye that I just barely started injecting at the start of the time period, and this is what I'm injecting right now. But then when the flow direction changes, this whole line gets pushed up. This is an entire, this is the dye that got injected. It got shifted, and this is where I'm continuing to inject the dye, and this is where it started. So this was at the beginning of injection. This is the point at which the flow direction changed, and then this is what's being injected right now.
Would it actually be like a sharp angle like that, or would it be like curved?
It would usually be curved. It would be tough to cause something to instantly change directions like that. But for purposes of simplifying, that's what they do. Now let me give you a caution, and that is that you may just, by looking at it, think that maybe the path line and the streak line are a mirror image of each other, and they're not. That's just coincidental in this diagram, that they somehow look like they're a mirror image. Don't let that coincidence throw you off and make you think that that's actually definitional. So let's work an example here. Take a piece of paper, a fresh piece of paper, and it works best if it's engineering paper because you can do it in increments. Each dot represents a single second maybe. But have the water flow to the right for 9 seconds, down for 4 seconds, and to the left for 6 seconds. And so you're going to draw a path line. The path line, so starting with that particle that's right here, the particle is moving according to these directions that are indicated. So draw the path line, and then I'll tell you how to draw the streak line. All right, so the path line I hope that you drew should look something like this, where it started at the upper left side, and then for 9 seconds the particle was moving to the right, so 1, 2, 3, 4, 5, 6, 7, 8, 9. And then it flowed down for 4 seconds, 1, 2, 3, 4. And then it flowed to the left for 6 seconds, 1, 2, 3, 4, 5, 6. And so if we were to trace the path line, we just connect the dots. And here's the path line. Now the streak line's a little bit different. The way to draw the streak line is, remember that we assume that the point of injection is not moving. That's what's changing is actually the flow itself, the flow field. The flow direction is changing. So I'm going to hold my hand steady, and I'm going to move the paper in the direction that's indicated by the arrows. And so if I start here, I need to move the paper to the right for 9 seconds. So 1, 2, 3, 4, 5, 6, 7, 8, 9. And then I need to move the paper down for 4 seconds. 1, 2, 3, 4. And then I need to move the paper to the left for 6 seconds. 1, 2, 3, 4, 5, 6. And this is the end, and this is the beginning of the streak line. Now again, it becomes more obvious that this isn't simply just that the streak line is the mirror image of the path line when the flow is moving at an angle. But that's the approach for how you draw the streak line, is you hold your pencil in the same spot and you move the paper around as though it was the flow field. Any questions about that? That's the method. All right. Acceleration, which we've talked about already today, consists of local acceleration, which is the change of velocity with respect to time, convective acceleration, which is the change of with respect to position, and there can also be tangential acceleration, which is when the direction of the velocity is changing. Rather than it being a change in speed, tangential acceleration is related to the position component or I'm sorry, the direction component of velocity. So even if if you have, for example, maybe you've tried this when you were a kid, like a coffee can full of water, and you tie it to a string and you start swinging it around, the water will stay inside of the can. And the reason why is even if you're swinging it at the same velocity, because there's an acceleration towards the center of the can, because it's a rotational flow that keeps the water inside of the can, because that acceleration is greater than the gravitational acceleration. So as a particle flows around a curve, there's a tangential component of acceleration, and you can break down the acceleration into its components in the x, y, and z direction with respect to position and time. And we've already looked at the local acceleration, where you've got a position changing with respect to time, and convective acceleration is what I told you, how the velocity may change as a function of position. And so if you consider this nozzle, where water enters the nozzle at 10 meters per second and exits the nozzle at 20 meters per second, that can happen on a constant basis, so that conditions aren't changing over time. That acceleration is due to convective, that change in velocity is due to convective acceleration. So it's the flow field itself that's accelerating the flow. And so if we compare uniform versus non-uniform to steady versus unsteady, what we'd say is that non-uniform flow exists when there's convective acceleration, and unsteady flow exists when there's a local acceleration. So it's the cause of those two. Let's do an example with convective acceleration. In this case, we have that same nozzle that was presented on the previous page, and it's 0.5 meters long. What if we wanted to calculate the convective acceleration at the point that is halfway between the entrance and the exit? You know, what is the rate that the velocity is changing at the center point there? So we're going to calculate the convective acceleration for the flow field. The formula for convective acceleration is the velocity times the change in velocity with respect to position. So here is the definition of convective acceleration. It has the variable a sub x. It's the velocity at a certain point multiplied by the change in velocity with respect to position. So here in this example, we're going to be interested in the midpoint, halfway between the entrance and the exit. If the entire L is 0.5 meters and we are at a point right here, then we're going to calculate the magnitude of the convective acceleration at the midpoint there. We have an equation that describes the change in velocity with respect to length. So this complicated looking equation is actually a lot simpler than it seems. What it means is that when x is equal to L, so when we exit the nozzle, then this will be 0.5, and so the initial entering velocity was 10, and it'll be divided by 1 minus 0.5. And so you can see how if the entrance velocity is 10, the exit velocity will be 20 meters per second when x is equal to L. And when x is equal to 0, so meaning at the entrance here, When x is equal to 0, then it'll just be the entrance velocity divided by 1. And so in between, this is going to be telling us how the velocity changes as a function of position. So this formula is the velocity relative to the inlet velocity as a function of how far into the nozzle L we are. So as you can see from the definition of convective acceleration, we're going to have to take the derivative of this equation with respect to x. And so let's start this off. We've got L is equal to 0.5 meters. X is equal to 0.25 meters. And the initial inlet velocity is 10 meters per second. We know that the convective acceleration, the A sub x, is u times du dx. Okay, so that is going to be the velocity (1 minus 0.5x divided by L) times 0.5 not L. Now, we got this from the chain rule. Let me just refresh your memory about the chain rule if it's been a while. If we need to find the derivative of this with respect to x, okay, so we know du dx is du dm times dm dx. So for u is u naught divided by 1 minus 0.5x divided by L. And we're going to let m, we're going to introduce some new variable we call m. That's going to be 1 minus 0.5x divided by L. And so u is going to be u naught divided by m. And so in other words, that is u naught m to the minus 1. Now if we applied the chain rule to that, then du dx is going to be d u naught m to the minus 1 divided by dm times d 1 minus 0.5x divided by L divided by dx. So that is minus 1 u naught m to the minus 2 times negative 0.5 divided by L. So where we're at so far is we introduced some variable m to stand in for the expression 1 minus 0.5x divided by L. Substituted that in. Since it's in the denominator, that's the same as u naught times m to the minus 1. We take the derivative of that with respect to m using the chain rule, and then it's dm dx. So for reintroducing what that m variable stands for m is 1 minus 0.5x divided by L, then du dx is negative 1 times u naught 1 minus 0.5x divided by L, that squared, times 0.5 divided by L. So that is 0.5 u naught times L minus 1 minus 0.5x divided by L squared. So we get into the weeds of the calculus there for a little while, but over here, what we're saying is we're going to take the derivative of the velocity function as a position, the velocity function as a function of position, trying to find out how the velocity changes as we move through this nozzle. And we can take the derivative of that with respect to x. So where this ends up is that expression that's at the end of our chain rule, which is 0.5 u naught squared divided by L1 minus 0.5x divided by L to the third power. Okay, and we substitute in for x is 0.25 meters. That's in the problem statement. It said that we want to find out what's the acceleration in the middle of the nozzle. So that's why we're using 0.25 as x. And the length, the overall length of the nozzle is given as 0.5 meters. So we'll substitute in those known values, and what we get is that u du dx is 0.5 u naught squared divided by 0.5 meters, 1 minus 0.5, and substitute in the 0.25 meters divided by 0.5 meters cubed. So what that works out to is u naught squared, because the 0.5 cancels out, and then 0.75 cubed. If we have 1 minus 0.25, basically, because the 0.5s cancel out there. So it is 2.37 u naught squared. And for the initial velocity of 10 meters per second, then the convective acceleration, a sub x, is going to be 2.37 times 10 meters per second squared. So it's 237 meters per second squared. And what you'll notice is that convective acceleration has the same units as local acceleration. Since it's an acceleration, it still has units of meters per second squared. But what that means is that here in the center of the nozzle, right here at this instant, not instant in time, but instant in position, right at this very location, the velocity is increasing 237 meters per second squared. All right, so that's all the time we have for today. Let's just take one final look at these announcements. Remember that the lab report for the floating bodies experiment is due in lab next Tuesday, and the homework assignment for the first part of Chapter 4 is due a week from today. So I'll see you on Tuesday.